Good evening, everyone. So let's just wait for 5 minutes so that if anyone wants to join, can join the class. So I hope you all must have gone through the lecture videos. Just wait for a few minutes. Okay, then let's start. You all can access the recording anytime you want. So I hope you all must have gone through the theory lecture videos. Today we'll be solving some problems related to the theory that you must have gone through. So let's start with the first question. Solve dy by dx minus y tangent x equals to 0. Sorry for the interruption. Uh, Let's continue. Okay. So we'll start with writing it as dy by dx equals to y tangent x. We can clearly see that the terms involving y variable and x variable can be separated, and this is a basic separation of variable type of problem. So we will write it as dy by y equals to tangent x dx. Now integrating both the sides, integrating both sides, we get ln y equals to ln secant x plus some constant, we'll take it to be ln c. So this gives us yx is equal to constant times secant x. So this gives us the solution. I hope this is fine with everyone. This does not need any kind of technicalities. So very easy kind of question. Okay, then let's move to the next question. Solve y square plus x minus 1 by y dy by dx is equal to 0. Here we can't say that we can separate the variables, or one might think that it is a kind of linear equation in variable x, because the maximum power of x here is 1. So let's try to convert this into this problem into dx by dy instead of dy by dx, and then solve it as the linear differential equations, the way we used to do. So solution, we have dy by dx times xy minus 1 by y equals to minus y square. This gives us dy by dx is equal to y cube upon 1 minus xy, which gives us dx by dy is equal to 1 minus xy by y cube. Now I'll write it more precisely in the form of the linear equation, plus 1 by y square x is equal to 1 by y cube. Now we all know how to solve such an equation. We start with integrating factor. So here the integrating factor would be, integrating factor is given by e to the power integral 1 by y square dy, which is e to the power minus 1 by y. And the general solution of star is given by x times integrating factor is equal to integrating factor times this function 1 by y cube dy plus some constant c. Now the main thing that we are left with is this integral. So to integrate it, we'll write it in a proper way. 1 upon y by y square, by y times 1 by y square dy plus c. Now we'll integrate it by substitution method. Let t is equal to 1 by y. This gives us dt is equal to, or we take it to be minus 1. This gives us dt equals to minus 1 by y square dy. So our integral is now e to the power minus t minus dt plus some constant c. Now we'll apply the product rule. Minus first term as it is, the integral of second term, minus derivative of t is 1, integral of e to the power minus t is minus e to the power minus t dt plus c. So this is t e to the power minus t minus e to the power minus t plus c. Therefore, we are left with x e to the power minus 1 by y is equal to 1 by y e to the power minus 1 by y, because what was t? T was 1 by y, plus e to the power minus 1 by y plus c. So we can write it as x is equal to 1 by y plus 1 plus c e to the power 1 by y. This gives us the solution. I hope you all followed the steps. I don't think there was any kind of technicality that was needed. The only important thing was to see that this equation turns out to be linear differential equation in variable x. And then using the standard method, we have solved this equation. Okay, then let's move to the next question. Question 3. Solve the initial value problem. So till now we were finding out the general solution where we had an arbitrary constant. Now we'll be finding the solution of initial value problem, where we'll be having some initial values which would help us to remove these arbitrary constant, and we would find basically a particular solution. Solve the initial value problem. X square y cube plus 2xy dy is equal to dx with the condition y at 1 is equal to 1. Solution. We'll start with again simplifying the equation. You can see from here that dx by dy is equal to x square y cube plus 2xy. So one can clearly see that it is of the form Bernoulli's equation. Let me show you how. Dx by dy plus minus 2y times x is equal to y cube times x square. So we all know a general Bernoulli's equation is of the form dx by dy plus some function of y times x is equal to some function of y times x power some n. This is a general Bernoulli's equation. So here our n is equal to 2. So how do we solve such an equation? We start with the substitution. We take t to be x to the power 1 minus n. So here n is 2. So we have 1 minus 2. That means minus 1. This gives us x is equal to 1 by t, and dt by dx, dt by dy is equal to minus 1 by x square dx by dy. And what is the value of x square? It's 1 by t. So we are left with minus t square dx by dy, which gives us, or we could directly imply, wait a second, we can directly imply from here that dx by dy is equal to minus 1 by t square dt by dy. So let's number this as 1, this one as 2. Using 2 in 1, we get minus 1 by t square dt by dy plus minus 2y by t is equal to y cube by t square. So simplifying it, we get dt by dy plus 2yt is equal to minus y cube. So now this is a linear differential equation in variable t. So again, we'll use the standard methods to solve the linear differential equation. We'll start with finding the integrating factor. So our integrating factor is integrating factor e to the power integration 2y, which is e to the power y square, and our general solution is t e to the power y square is equal to integration minus y cube e to the power y square dy plus c, which is equal to minus integration y square e to the power y square 2y dy 1 by 2 plus c. Why did we write it like this? So that we can use the substitution. We'll take some other variable v to be equal to y square, and then we'll get 2y dy to be dv. So let y square is equal to v. We get 2y dy is equal to dv. This gives us minus 1 by 2 integration v e to the power v dv plus c. Now again we'll be using the product rule to solve this integral. This gives us v as it is. Integral of e to the power v is v minus integration of derivative of v is 1 e to the power v, and we know that the integral of e to the power v is again e to the power v, so we'll write it directly plus c. Now substituting the value of v, what was v? It was y square minus e to the power y square minus 1 by 2 plus c, and on the left hand side we had t e to the power y square. This gives us t is equal to 1 minus y square by 2 plus c e to the power minus y square. Now what was t? T was 1 by x. So our solution is 1 by x is equal to 1 minus y square by 2 plus c e to the power minus y square. Now this was our general solution. We need to find the solution of the initial value problem. So we have condition y at 1 is equal to 1. This gives us 1 is equal to 0 plus c e to the power minus 1. This gives us c is equal to e. Therefore, our particular solution is 1 by x is equal to 1 minus y square by 2 plus e to the power 1 minus y square. This is our final solution. Okay. I hope the solution was fine with everyone. The main important thing here is that we at the end we need to use this initial value so that we get the particular solution. Rest we had used the basic method to solve a Bernoulli's equation. So now let's move to the next question. Question 4. Solve x cube plus xy power 4 dx plus 2y cube dy is equal to 0. So if we consider this function to be some mxy and this one to be some nxy, what do we have? Solution. Let mxy is equal to x cube plus xy power 4. Let's number it 1. This implies partial derivative of m with respect to y is 4xy cube. And let nxy to be 2y cube. This gives us the partial derivative of n with respect to x is equal to 0. Clearly, this is not an exact equation. Therefore, my is not equal to nx implies first is not an exact equation. Now let us see whether we can find an integrating factor. If we can find an integrating factor, then that would be a very good opportunity for us so that we can easily solve this problem. So how should one start to look for integrating factor? So the first thing that one should look for is this function my minus nx by n. Now if this turns out to be a function in x, a function only in one variable x, then we can find with the integrating factor. Now this is equal to 2y cube minus 0 by what is n? 4xy cube. So we are left with 1 by 2x. Now this is a function with only one variable x. This is a function only in x. So this implies our integrating factor is given by, we have the integrating factor is equal to e to the power integral of 1 by 2x dx, which is equal to e to the power 1 by 2 ln x, which is basically okay. I think I did some mistake. My is 4x cube. So my is 4. Okay. My is 4xy cube minus 0 by n is 2y cube. So I just replaced my and n. Again, we all here also we have the function, the value in only in x, but this would be 2x. So this changes. This is 2x dx, which gives us e to the power x square. Our integrating factor is e to the power x square. This implies e to the power x square mxy dx plus nxy dy is equal to 0 is exact. Let us see. That is e to the power x square, that was n, x cube plus xy power 4 dx plus e to the power x square 2y cube dy is equal to 0 or is exact. Or x cube e to the power x square plus xy power 4 e power x square dx plus 2y cube e to the power x square dy is equal to 0 is exact. You can clearly see that if we take this to be m bar and this to be some n bar, then m bar y is 4xy cube e to the power x square and n bar x is equal to 4xy cube e to the power x square, which are same. So since this is an exact equation, we have its solution. Let's number this as we given as equation 2. This implies the solution for equation 2 is given by fxy equals to c, where f is a function such that fx is equal to m bar. That was x cube e to the power x square plus x y to the power 4 e power x square, and fy is equal to 2y cube e to the power x square. Now from here, let's number this as third, this one as fourth. From fourth, we get fxy is equal to integral of this function with respect to y. So this gives us 2y to the power 4 by 4. So y to the power 4 e power x square by 2 plus some function of x. This gives us f derivative of f with respect partial derivative of f with respect to x is equal to 2x y power 4 e power x square by 2 plus g dash x. Now from fourth and fifth, sorry, from third and fifth, what do we get? Now these two and 2 gets cancelled out. This term and this term will get cancelled out. We'll be left with g dash x is equal to x cube e to the power x square. This implies gx is equal to integral x cube e to the power x square, which is x 2 1 by 2 e to the power x square dx. Now let t is equal to x square. We get dt equals to 2x dx. So this gives us gx is equal to 1 by 2 integration e to the power t dt. Again, we'll be using product rule to integrate it. T as it is, e to the power t minus e to the power t. E to the power t minus 1 by 2. Now what was t? It was x square. Gx is equal to e to the power x square minus 1 by 2. Therefore, by equation, let's number this as star. By star, we have fxy is equal to y power 4 e power x square by 2 plus x square minus 1 e power x square by 2. Therefore, our general solution is given by, therefore, general solution for equation 2 is to that way only. Equation 2, and hence for 1 is given by y power 4 e power x square by 2 plus x square minus e power x square by 2 equals to some constant, or we can simplify it to be e power x square y power 4 plus x square minus 1 is equal to c. So I hope all the steps were clear enough. We have mainly found the integrating factor. The main important thing in this solution was to identify whether this is a function of x or not. If it wasn't a function just in variable x, then we could not have found the integrating factor. Well, in that case we would look for some other things. For example, we can see that if my minus nx by m is a function in y, then in a similar way we can find the integrating factor. Or there are various other methods that you must have seen in the theory classes. Okay, then let's move to the next question. Question number 5. Solve x dy by dx plus y equals to y square log x. We can see that we have a y and a y square. So we can convert this problem into a Bernoulli's equation. Let's see how. Solution. So from here we get dy by dx, dividing both the sides by x, we get 1 by x times y is equal to log x by x times y square. Now we are in the framework of Bernoulli's equation. So how do we start to solve a Bernoulli's equation? We start with the substitution. T equals to y to the power 1 minus n. This is n. So here n is equal to 2. 1 minus 2 means minus 1. So we have y is equal to y is equal to 1 by t, which gives us dy by dx is equal to minus 1 by t square dt by dx. Now I'll number this as 1, this as 2. Using 2 in 1, we get minus 1 by t square by dx plus, what was 1 by x? 1 by x is as it is. What was y? 1 by t. So it's 1 by xt is equal to log x by x, and what's y square? 1 by t square. Now multiplying both the sides by minus t square, we get dt by dx minus t by x is equal to minus log x by x. So now we are in the framework of linear equation. This is a linear differential equation in variable t. So how do we start? We start with then integrating factor. So here the integrating factor is given by e to the power integral minus 1 by x dx, which is e to the power minus ln x, which is 1 by x. So with this integrating factor, we get our general solution as t times the integrating factor is equal to integrating factor times the function minus log x by x plus some constant c. Now this is minus integration log x times 1 by x square dx plus c. Here also we will use the product rule, or what do we say, integration by parts, to solve this integral, which gives us minus log x as it is. Integral of 1 by x square is minus 1 by x minus integral of derivative of log x is 1 by x. Integral of 1 by x square minus 1 by x dx plus c. So this gives us log x plus x minus integration of 1 by x square is minus 1 by x plus c. So we have t is equal to, multiplying both sides with x, t is equal to log x plus 1 plus cx. And what was t? T was 1 by y. Substituting the value of t here, we get 1 by y is equal to log x plus 1 plus cx. So this is a solution. So I hope all the steps in this solution were fine with everyone. If you have any doubt, you can just let me know. Okay, then let's move to the next question. Till now we have been solving, just solving the equations using specific methods. Next we will be analyzing the solution. So we'll be doing some kind of analysis. So first let me write down the question. It states that show that two solutions y1 and y2 of the second order homogeneous linear differential equation given by ax y double dash plus bx y dash plus cx y is equal to 0. Let's number this one as star, where a, b and c are continuous real valued functions with a non-zero, clearly, because if a turns out to be 0 we would lead back to the first order differential equation. But now we want to analyze the second order differential equations on a less than equal to x less than equal to b. So our domain for the problem is closed interval a to b, are linearly dependent linearly dependent on the domain a to b if and only if the Wronskian of y1 and y2 is 0 for all x in. So, some major things that one should know before solving such a question is, what do we mean by if and only if? How do we calculate Wronskian? And what do we mean by linearly dependent? So let's start with Wronskian. We know that Wronskian for any two functions y1 and y2 is given by the value of determinant y1, y2, y1 dash, y2 dash. The value of this determinant gives us the Wronskian. Next, what do we mean by linearly dependent? We say that f and g are linearly dependent if there exists some constant k such that f is equal to k times g, or fx is equal to k times gx for every x. So for every x, this k must be unique. If such a constant k exists, or we can say that there exists some constants k1 and k2 such that k1f plus k2g is equal to 0, then we say that with k1, k2 non-zero, we say that f and g are linearly dependent. The next major important thing is this if and only if. So when we have to prove if and only if, suppose we have two statements P and Q, we need to prove that P if and only if Q. Here, what are the two statements? The first statement is that y1 and y2 are linearly dependent, and the second statement Q is that the Wronskian of y1 and y2 is 0. So to prove that P if and only if Q, we need to prove that P implies Q and Q implies P. That means, firstly, we will start with the fact that y1 and y2 are linearly dependent. Then we will show that their Wronskian, that this would imply that the Wronskian is 0. And conversely, we need to show that if the Wronskian is 0, this would imply that the functions y1 and y2 are linearly dependent. I hope you all are now comfortable with the setup of the question. We need to show that if y1 and y2 are two solutions of the function of the differential equation star, firstly we'll assume them to be linearly dependent and prove that the Wronskian is 0. Then conversely, we will start with the fact taking that Wronskian of y1 and y2 is 0 for all x, and hence that must imply that the functions y1 and y2 are linearly dependent. Okay, let's start with the solution. Let y1 and y2 be two solutions of the equation star. Suppose the Wronskian of y1, y2 is equal to 0 on closed interval AB. That means the determinant y1x, y2x, y1 dash x, y2 dash x is equal to 0 for every x in close AB. So this would imply, now let x naught belonging to closed interval AB be some arbitrary point. Now since the determinant is 0 for all x, it must be 0 for x equals to x naught as well. So this implies y1 x naught, y2 dash x naught minus y2 x naught, y1 dash x naught is equal to 0. Okay, so now let's consider the system. Consider the system of equations C1 y1 x naught plus C2 y2 x naught is equal to 0, and the second equation C1 y1 dash x naught plus C2 y2 dash x naught equals to 0. We all know that we can write this system as some product of matrices y1 x naught, y2 x naught, y1 dash x naught, y2 dash x naught times c1 c2 is equal to 0. This is a homogeneous system of equation, and we know that there exists non-trivial solution to this problem. That means there exists c1 c2 non-zero if and only if the determinant of this matrix is 0. And we know here, since the Wronskian at x naught, which was this determinant itself, since Wronskian y1 y2 at x naught is equal to 0, this implies first must have a non-trivial solution. That means there exist unique C1 and C2 non-zero. They need not be unique. There exists C1 and C2 non-zero satisfying the system 1. Now let fx is equal to c1 y1x plus c2 y2x. We will show that fx is equal to 0, because if fx is equal to 0, that gives us y1 and y2 are linearly dependent. So this gives us fx naught is equal to c1 y1 x naught plus c2 y2 x naught, which was 0 because c1 c2 is solution of the system 1. And similarly, f dash x naught is equal to c1 y1 dash x naught plus c2 y2 dash x naught is equal to 0. Therefore, we have fx naught is equal to 0 and f dash. Now, let me recall a theorem that you must have gone through, which states that theorem, let ax y double dash plus bx y dash plus cx y is equal to 0 with ax non-zero for all x in close interval ab. Let belonging to ab belongs to ab, c1 and c2 are two constants, then there exists unique solution f of this equation. Let me mark it as hash. Unique solution f of hash such that f at x naught is equal to c1 and f dash at x naught is equal to c2. That means there exists one and only one function, only one solution of equation hash such that this function takes value at x naught is equal to c and its derivative is at x naught is c2. Particularly, in particular, if c1 is equal to 0 is equal to c2, this implies there exists unique solution to hash such that f x naught is equal to 0 is equal to f dash x naught. Also also we know that if we take the function g to be trivially 0, implies gx naught is equal to 0 is equal to g dash x naught. But what does the theorem says? The solution must be unique. This implies by uniqueness g must be, sorry, f f must be equal to 0. So we will be using this theorem. Using this theorem, we get, here also we have f x naught equals to 0, f dash x naught equals to 0. This implies by implies by uniqueness result f must be equal to 0. And what was f? F was c1y1 plus c2y2. This gives us c1y1x plus c2y2x is equal to 0 for every x in AB. Therefore, this was the definition of, this was the definition of linearly dependent, because C1 and C2 are non-zero. Therefore, Y1 and Y2 are linearly dependent. So what are linearly dependent? So what do we have now? We have that if the Wronskian is 0 for every x in AB, that must imply that Y1 and Y2 must be linearly independent. Now we'll see the converse part. Converse part is still not that tricky. The main important thing here was to prove that Wronskian 0 implies that the functions y1 and y2 must be linearly dependent. And for that, what had be done, we took a point x naught and a function f to be c1 y1 plus c2 y2, and these c1 c2 existed because of the fact that Wronskian is 0. We had some non-trivial c1 and c2, and using that c1 c2 we constructed a function f to be c1 y1 plus c2 y2. Using the value of function f and its derivative at x naught and this theorem, uniqueness theorem, we got that f must be 0 and hence y1 and y2 must be linearly dependent. I hope it was clear. Now let's see the converse part. Let us assume y1 and y2 are linearly dependent. We need to show that their Wronskian is 0. Now since they are linearly dependent, this implies there exists C1 C2 non-zero such that C1 y1 plus C2 y2 is equal to 0. This implies C1 y1 dash plus C2 y2 dash is equal to 0. This implies the system y1 y2 dash y2 dash C1 C2 is equal to 0 0 has a non-trivial solution. Non-trivial solution. This implies the determinant y1x, y2x, y1 dash x, y2 dash x is 0, which is for every x in AB, which is the Wronskian of y1 and y2 at point x is equal to 0 for every x in AB. Or from here we can write Wronskian of y1, y2 is trivially 0. So I hope this converse part was clear. We didn't have to use any technicalities to prove it. All we needed to know is the fact that a system of homogeneous equation ax is equal to 0 has a non-trivial solution if and only if determinant of a is 0. I hope you all must have seen this in your school time. Okay. So let's move to the next question. Question 6. Consider the differential equation given in question 6. That is the equation star. What was star? Star was axy double dash plus bxy dash plus cxy equals to 0. A general second order homogeneous linear differential equation. Okay. Star. Then every solution of star can be expressed as a suitable linear combination. Linear combination C1y1 plus C2y2 of 2 L is 2 linearly independent solutions of star. That means the question wants us to show that a general solution, any solution of the problem star, can be written as a linear combination. Linear combination means some constant times y1 plus some constant times y2 of two functions, linear combination of y1 and y2, where y1 and y2 are two linearly independent solutions. Now, what do we mean by linearly independent solutions? Earlier, we have seen linearly dependent. So, what comes in our mind? That something which the functions that are not linearly dependent are linearly independent. Or we can say two functions f and g are said to be linearly independent if C1f plus C2g is equal to 0 must imply C1 is equal to 0 is equal to C2. Because if either of them is non-zero, it turns out to be linearly dependent. We had seen earlier by the definition, if C1 and C2 are non-zero, then they must be linearly independent. Okay, I'll wait for 5 minutes for you to try this question. You can just start with a general solution of star, then look at the Wronskian of y1 and y2. So what do you think? What should be the Wronskian of y1 and y2 when y1 and y2 are linearly independent? Okay, then let's start. Solution. We know that if y1 and y2 are linearly dependent, then the Wronskian must be 0. Also the converse part. Now we have y1 and y2 are linearly independent. That means they are not linearly dependent. That means the Wronskian must be non-zero. Let y1 and y2 be two linearly independent solutions of star. This implies by question 6, Wronskian of y1 and y2 must be non-zero. Because if the Wronskian is 0, that must imply that y1 and y2 are linearly dependent. But we have the opposite. We have y1 and y2 are linearly independent. So this gives that the determinant, this implies there exists, this implies there exists some x naught in AB such that Wronskian of y1 and y2 at this x naught is non-zero. That means this determinant y1x, y2x naught, y1 dash x naught, y2 dash x naught is non-zero. Now consider, now let f be any solution of star. What do we want? We want that f should be of the form of linear combination of y1 and y2. So consider the system. Consider the system y x naught plus c2 y2 x naught is equal to fx naught, c1 y1 dash x naught plus c2 y2 dash x naught is equal to f dash x naught. If we write it in the form of matrices, we can write it as y1 x naught, y2 x naught, y1 dash y2 dash x naught, c1 c2 is equal to fx naught, f dash x naught. Now we are in the framework of non-homogeneous system of equations. Now since this determinant, if we take this to be to be a matrix A, since determinant A is non-zero, the system, let's number it as 1. This implies the system 1 has unique solution. This implies there exist unique C1 and C2 such that fx naught is equal to C1 y1 x naught plus C2 y2 x naught. Now this is a fixed real number. I will take it as k1. And f dash x naught is equal to C1 y1 dash x naught plus C2 y2 dash x naught. I will take it to be k2. Now what do we have? The uniqueness theorem. Uniqueness theorem says that there exists unique solution. That means f is one and only one solution such that fx naught is equal to k1 and f dash x naught is equal to k2. But we know that if y1 and y2 are solution, then c1y1 plus c2y2 is also a solution. If I take this function to be g, what do we get? G dash x naught, sorry, gx naught is c1 y1 x naught plus c2 y2 x naught, which is equal to k1, and g dash x naught is equal to c1 y1 dash x naught plus c2 y2 dash x naught, which is equal to k2. This gives us, if this implies by uniqueness result, f must be equal to g. That means f x is equal to gx, which is equal to c1 y1 x plus c2 y2 x for every x in AB. That is what we wanted. We wanted, now since f was an arbitrary solution, an arbitrary solution is a linear combination of y1 and y2. That is what we wanted, and hence we are done. Hence, we are. So the main important result again here was the uniqueness result. Uniqueness result states that there exists one and only one, there exists unique solution to the second order linear homogeneous differential equation satisfying some gx not equals to k and k1 and g dash x not equals to k2. And hence we get that any solution of star can be found using two linearly independent solutions. So what does we get? We get that if we can find any two linearly independent solutions to a second order linear homogeneous equation, then we can find all the solutions. Isn't that great? With the help of just two solutions, we can find all infinitely many solutions. Now let's get back to problem solving. I hope it was um, enough of analysis. It must have been blown your mind. But yes, this is the beauty of mathematics. This is the main mathematics that we all, especially the researchers, love. Okay, then let's move to next question number 8. Find the general solution of the second order equation x y double dash minus 2x plus 1y dash plus x plus 1y is equal to 0. Let me mark it as 1. Knowing that an exponential function is a solution. Is a solution. That means we are given that an exponential function is a solution to this problem. Now, if we can find second solution, then using these two solutions, second linearly independent solution. We already have that e to the power x is a solution. We are given that this is a solution to equation first. If we can find some y2 such that these functions are linearly independent, then we can find a general solution to the problem 1. So Before solving this question, let me recall Abel's formula. For the second order homogeneous linear differential equation, of the form y double dash plus px y dash plus qx y equals to 0. The Wronskian if y1 and y2 are two Li solutions, then Wronskian of y1 and y2 is given by e to the power integration px dx. So we'll be using this Abel's formula to find the Wronskian, and using the value of Wronskian we'll find the second solution. So let's start with the solution. We are given that y1 is equal to some cons e to the power x is a solution of equation 1. And by Abel's formula, we have Wronskian of y1 y2 is equal to e to the power integration. What is px here? Once we divide the equation by x, we get px to be minus 2x minus 1 by x. This is, sorry, in this formula here we had minus. So we will have 2x plus 1 by 2, sorry, x dx, which gives us e to the power 2x plus ln x, which is, oh, I'm so sorry, this must have a constant. C, we have c x e to the power 2x, where y2 is a solution of first, such that y1 and y2 is Li. Also, by the formula of Wronskian, what do we have? We have y1x, y2x, y1 dash x, y2 dash x is equal to cx e to the power 2x. This gives us, what was y1? It's e power x y2 dash x minus y2x times y1 dash x. So we know that the derivative of e power x is e power x itself. So we have y2x is equal to c1x e to the power 2x. This gives us y2 dash minus y2 is equal to c1x e to the power x. Now this is again a differential equation, but of first order. We can solve a first order differential equation of this form. This is dy2 by dx minus y2 is equal to c1x e to the power x. This is a linear differential equation. So we have the integrating factor e to the power minus integration y2, sorry, minus 1 dx, which is e to the power minus x, and its solution is given by y2 times integrating factor is equal to integration c1x e to the power x e to the power minus x dx plus some constant c2. So this gives us c1x square, or we can write it as c2x square, where c2 is just c1 by 2, okay, c3 plus c2. This gives us y2x is equal to c2 e to the power x plus c3 x square e to the power x. Therefore, our general solution is yx is equal to k1 times y1x. y1x was e power x plus k2 times c2 e power x plus c3 x square e power x, which can be clubbed together and we can write it as a e power x plus b x square e power x by x. This is the general solution. Clearly, e power x and x square e power x are linearly independent. So these were the two linearly independent solutions, and their linear combinations will give us the whole set of solutions. Now let's move to the next question. Question 9. Find general solution of y double dash plus 3y dash minus 54 y equals to 0. Solution. We solve such problem by starting with a trial function. We take, let yx is equal to e to the power ax be a trial solution. We will see whether this would work or not. So this implies y double dash, sorry, this implies e power ax a square plus 3a e power ax minus 54 e power ax is equal to 0. This implies power ax a square plus 3a minus 54 is equal to 0. Now since e power ax is never 0, we know that exponential function tends to 0 but never attains the value 0. This implies a square plus 3a minus 54 is equal to 0. Now solving this quadratic equation, we get a is equal to minus 3 plus minus under root 9 plus 216 by 2, which is minus 3 plus minus 15 by 2, which is minus 9 or 6. So if we take a to be minus 9 or 6, then yx is equal to e to the power ax will turn out to be the solution. Therefore, y1x is equal to e power minus 9x and y2x equal to e power 6x are solutions of problem 1. Now since y1 and y2 are linearly independent, general solution is given by, we have the general solution yx is equal to c1 y1 x plus c2 y2 x, which is c1 e to the power minus 9x plus c2 e power 6x. So this gives us the general solution. I hope all the steps were fine with this discussion. Such problems are solved using trial function, and this equation, this quadratic equation, is called the auxiliary equation. So from next time, we won't be starting with function yx to b power ax, because eventually we will end up with the same kind of scenario. We will start with the auxiliary equation, and further we will see the what are the roots of the auxiliary equation. You must have seen in the theory classes that based on the value of the based on the properties of roots of this auxiliary equation, we have different kind of solution. The first case is of the first case is when we have distinct roots. For example, the case we had here, the distinct real roots. In that case, we have the solution directly in this form. And then you must have seen what happens for the case when we have repeated roots and complex roots. So let's see one question where we would be having some complex roots, and we'll see how the solution would look like in that case. So this is the last question for today's lecture. Find the solution of the initial value problem y double dash minus 6y dash plus 13y is equal to 0, with y0 equals to 1, y dash 0 is equal to 1. You must have observed that while solving initial value problem of first order, we needed just one initial value. But in the case of second order, since we will be having two arbitrary constant, we need two initial values. Okay. So here I'll directly jump to the auxiliary equation. You all can easily see that the auxiliary equation would be given by for first is given by a square minus 6a plus 13 is equal to 0. So now we can solve this quadratic equation. We get a is equal to 6 plus minus under root 36 minus 52 by 2, which gives us 6 plus minus root 16 by 2 root minus 16, which is 3 plus minus 2 root 2 iota. So we have complex root, and in the case of complex roots, the general solution is given by yx is equal to e to the power 3x times c1 cos 2x plus c2 sin 2x. Basically, if a is equal to sum a1 plus minus iota a is equal to sum b1 plus minus iota b2, in that case our solution is e to the power real part times x plus c1 cos imaginary part times x plus c2 times sine imaginary part x. So the general solution is given like this. So this gives us our general solution. Now what's the next step? We need to find the particular solution because we have initial values. Now since y at 0 is equal to 1, this implies, so putting the value of x equals to 0 in the equation second, we get e to the power 0 c1 plus 0 is equal to 1. This implies c1 is equal to 1. This implies our yx was e power 3x cos 2x plus c2 sin 2x. Now let's differentiate it. Y dash x is equal to, we'll be using the product rule to differentiate, e to the power 3x as it is. Derivative of cos x is minus sin x, and so derivative of 2x is 2, plus c2 times derivative of sin 2x is cos 2x, plus the second term as it is, plus c2 sin 2x. And what is the derivative of e to the power 3x? 3 times e to the power 3x. Now this implies y dash 0 is equal to e to the power 0 c2 plus 0 plus 3 e to the power 0 1 plus 0, which is c2 plus 3. It should be 2 cos x. Huh? So we should have 2c2. So we were given that y dash 0 is equal to 0. This implies, sorry, y dash 0 is equal to 1. Y dash 0 is equal to 1. This implies 2c2 plus 3 is equal to 1, implies it's equal to minus 1. Therefore, putting the value of c1 and c2 in the expression for y given in equation 2, we get yx is equal to e power 3x cos x cos 2x minus sin 2x. So this gives us the particular solution. I hope you all were fine with all the steps throughout the questions. I will be uploading this lecture video on YouTube. You all can easily access it, and please let me know in the comment section or any by mail anyway, in any method you can tell me if you have any doubt. Okay then. Thank you.